Welcome back to Physics with Miyoshi. Today we're going to talk about a little bit more about ideal gas law, and we're going to talk about the kinetic theory of gases so we can tie up we're going to see if we can check out the macroscopic, in other words, things you can observe, to the microscopic, the things we can't observe with our eye, particles bouncing around and how they affect each other. So we're going to use Newton's laws, talk about particles. We can represent a particle, something like this ball, and the ideal gas law to figure out how the kinetic energy is related to the temperature. So if we think about any space, we can think about our particles hitting against walls, and if I hit this particle hits this wall, we know through Newton's laws and through impulse momentum theory that it does impart a force on there. As a matter of fact, and we know that the particles don't all hit the same way, but they bounce all over the place, and they're all doing their own thing. But they impart a force on there, which in turn creates a pressure. And we're going to talk about how that average kinetic energy, if we think about the average kinetic energy for a single particle in an ideal gas, is related to the temperature, something we can actually measure. And so we can see through this equation, kinetic energy of a single particle in ideal gas is 3/2 K, which is Boltzmann's constant, times our temperature in Kelvin. So Boltzmann's constant again is 1.38 times 10 to the negative 23rd. And that is really just our ideal gas constant divided by Avogadro's number. We're also going to look at the internal energy work. We're going to derive this equation a little bit, and we're also going to look at the internal energy in an ideal gas. We're just going to throw that out there. The internal energy is 3/2 N, which is the number of moles, the number of molecules in moles, times R, which is the ideal gas constant, times the T, which is again the temperature in Kelvin. The ideal gas constant is again 8.31 joules per mole Kelvin. Okay, so if we want to look at the theory about this whole behind this kinetic energy, finding the kinetic energy of average kinetic energy of a single particle as it moves around in our ideal gas, we can look at a single particle, and if we look at this little graph over here, this is what Maxwell, a guy named Maxwell, he came up with this distribution, and you can see this distribution all over in nature. And if you think about even grades, oftentimes in a class, they follow what's called a bell curve or a Maxwell curve like this, where we have a probability or a percentage of speed, and this would be lots of particles going through in our little box here that's L by L by L. But they would have, depending on the temperature, we know that the probable speed is going to be at the top here, and then as it falls off, there's going to be a few particles down here at 0 or near 0, and a few particles up here at a higher place somewhere. And we can see that Maxwell found these out, that in oxygen, if I have 1200 Kelvin, there's a probable speed of around 800 meters per second. If I have oxygen at 300 Kelvin, then it's got a probable speed of around 400 meters per second. That's what we call, later we'll talk about that, is that probable speed is called our speed RMS, or VRMS, root mean square speed. We'll talk about that in a minute. So, if we think about this box, it's got L by L by L length, height, and width. It's a cube. And we think about a single molecule in there. So this molecule is going to bounce and hit this wall over here. If it hits the wall at V, a speed V, a positive V going to the right, then it's going to bounce off at a speed of negative V, coming back the other way. It's got a elastic collision, and so it's got some momentum coming in, it's got some momentum coming out, and that momentum is what's going to create the force, especially if there's millions of particles hitting there over and over and over again. So we find that the average force is going to be the final momentum minus the initial momentum divided by our time, and that's just through the impulse momentum theorem. We also know, by knowing the length of this guy and knowing the speed that it's going, that the time that it's going to take to go from the wall to the wall is, in fact, 2L divided by V. And we can figure that out just looking at the distance is going back and forth. And so that time is going to take to go back and forth between here is going to be our distance divided by our speed. So if we look at this, our final momentum is mv, m times v coming in. It's going that way. And then our initial momentum is mv, it's going this way. So we subtract the 2 and divide that by 2L over v, and we end up getting negative mv squared over L. Well, this v is just a single particle, and so we'll talk about that. Well, I get ahead of myself here a little bit. But if we look at the wall, the third law says that the force that the wall is imparting, or that the force on the wall then is going to be the opposite of this guy, which is mv squared over L. Now v, in this case, we're going to take the average v, or the average v squared of this guy, and that's where this probable speed comes in. And that's going to be called our VRMS, our root mean squared speed. The other thing that's kind of interesting about this equation, if we think about all 3 dimensions, and we think about all the different particles in there, about a third are going in the x direction, a third are going in the y direction, a third are going in the z direction. So that's where this 3 comes in. So F is our number of molecules divided by 3 times our mass of a single particle times our root mean squared velocity divided by L. And again, this comes from our individual particle. That's the force that an individual particle exerts, and our force that are now totally exerting on there are from all of our particles is again this n over 3 mv squared over L. And again, this is our V RMS, so we're going to substitute that back in here. If we think about pressure, pressure is force over our area. So the area of this side of the box is L times L. So now we have the force divided by L squared. That's our pressure, and that's going to be N over 3 divided by mv squared, or VRMS squared, divided by L cubed. So now that we have the L squared times the L is going to give us our L cubed. Now, what's L cubed? Well, L cubed is just the volume of this whole guy. So now what we're going to do is we're going to multiply this guy by the volume, and we can see that P times V, our pressure times our volume, is 1/3 N times mv RMS squared. Now this looks really familiar if you think about it. mv squared looks like kinetic energy, right? The only thing that's missing is the half. So if I multiplied this by half and multiplied it by 2, that's the same as multiplying it by 1, right? So 2 over 2 is 1. So I can look at this and change this equation just slightly and say that my pressure times my velocity is 2/3 N. So I multiply it by the 2. And that's times 1/2 mv RMS squared. So I divide it by 2. It's the same equation. I just multiplied by 1. In this case, 2 over 2 is 1. Well, this now looks like kinetic energy, and we can think about it since it's the RMS value of the V, our velocity, root mean squared velocity squared. That is our kinetic energy. That's our average kinetic energy of a single particle. So if I take the average kinetic energy of a single particle, multiply that by my number of particles, multiply that by 2/3, I'll get my pressure times velocity. So, well, what does that have to do with anything? Well, if I think about back to PV is NKT, which is our ideal gas formula, then that's equal to this guy still. So now I have N times K times T is 2/3 N times the average kinetic energy. Well, if I divide both the ends out, then I have my kinetic energy, 2/3 of kinetic energy is K times T. Well, if I rearrange that equation just a little bit, multiply both sides by 2/3 or 3/2, then I end up getting this kinetic energy. The average kinetic energy is 3/2 my Boltzmann's constant, K times T, my temperature in Kelvin. And that's what we had up here. I just wanted to show you how that all happens, and going from a single particle bouncing back and forth against the wall, creating pressure or creating force, and then that creating pressure against that wall, how that turns out to show us that I can find the average kinetic energy of all my molecules simply by knowing the temperature and multiplying that by my Boltzmann's constant and this number 3/2. So there you have it. There's a little derivation, a little bit about distribution of our different speeds in there. And again, remember that the speeds in here of our different molecules are going all over the place. About a third of them are going in the x direction, a third of them going in the y direction, a third going in the z direction. That number that shows up right there, and it's a little bit confusing sometimes, but that's where that number 3 comes. But anyway, a little bit more about ideal gas, average kinetic energy of particles, a little bit about the internal energy of an ideal gas, again related to our this equation here. Kinetic energy average is 3/2 k times T, and the internal energy of an ideal gas is 3/2 n times R times T. So a little bit about the kinetic theory of ideal gases, hopefully reconciling Newton's laws and particles and ideal gas law to find these couple nifty equations for us to use with ideal gases. So thanks for tuning in, and we'll see you again for more Physics with Miyoshi. Bye-bye.